So we're now going to try to evaluate the Fourier transform of a periodic signal in which we will not use the Euler's expansion, but rather rely on the Fourier series representation directly. The example that the problem statement is to determine the Fourier transform of the strain of impulses, and the train of impulses is located capital N samples apart. In order for me to determine the DTFT, the first thing I need to do is to determine the Fourier series representation. So I know that x of n, because it's periodic, can be represented in its Fourier form. Fourier representations is ak e raised by j k 2 pi divided by capital N times n, and let this summation be from 0 to capital N minus 1, where each one of the Fourier series coefficients can be determined through the analysis equation. So this is 1 upon n summation. Let this be from 0 to n minus 1 x of n e raised to power minus j k 2 pi divided by n times small n. And since this summation is from this particular summation is from 0 to capital N minus 1, and since it's a train of impulses, and within this interval of summation, there's only going to be one impulse that's going to be there. So this is really delta of n here within this interval, and it's pretty straightforward. I mean, this comes out to be equal to, from the shifting property of the delta function, this turns out to be equal to 1 upon n. So our conclusion, therefore, is that the train of impulses can actually be represented in its Fourier series form as a simple sum of complex exponentials. This is 1 upon n. All of the Fourier series coefficients are the same, and this is summation from k equals 0 to capital N minus 1, and then e raised to power j k 2 pi by capital N times small n. Now, in order for me to find the Fourier transform for this, I just rely on the fact that the Fourier transform for e raised by jk 2 pi by n, capital N, is just an impulse. And this k times 2 pi by n is always going to reside in the interval from 0 to 2 pi. So in other words, so e raised to power j k times 2 pi by n times n, and just plug in a 1 upon n outside as well. I know that if I take the Fourier transform for this, within the interval in the frequency between 0 and 2 pi, so this is 0 and this is 2 pi, this is going to be an impulse, which is just residing at k times 2 pi by capital N, where of course k is between 0 and capital N minus 1. And that's why it's between 0 and 2 pi in the frequency domain. And the height, of course, is going to be 2 pi by capital N. And therefore, just using the linearity property, I can conclude that Fourier transform of x of e raised to power j omega is just simply going to be a train of impulses as well between 0 and 2 pi. So if this is the, so let's say this is 0 and this is 2 pi, I'm going to get the first impulse at 0, the second impulse just 2 pi by n apart, the third impulse, and so on and so forth. And the final impulse is going to be here. So this is 2 pi by n. This is 2 times 2 pi by n. And the final impulse is going to be at, this is at n minus 1 times 2 pi by n. And of course, the heights for each one of these impulses is going to be 2 pi by n. This is 2 pi by n. All of these heights are going to be 2 pi by n. And just to once again make it clear, this impulse is actually the Fourier transform of 1 upon n e raised to power j times 0. Similarly, this impulse is the Fourier transform of 1 upon n e raised to power j 1 times 2 pi by n times n. Similarly, this is the Fourier transform of 1 upon n e raised to power j 2 times 2 pi by n times n, and so on and so forth. Similarly, this is the Fourier transform 1 upon n e raised by j capital N minus 1 2 pi by capital N times. And then of course, all of these chain of impulses periodically repeat themselves. So that's implicit. I am not going to, so that's implicit. So let me, yeah. So this actually repeats itself because of the periodicity and so on and so forth. So just by looking at this graph what I can immediately conclude is that x of e raised by j omega is also a train of impulses. And mathematically, I can write that as 2 pi by n because each impulse is of height 2 pi by n, summation k going from minus infinity to plus infinity delta omega minus k times 2 pi by n. So that's the Fourier transform of it. So the train of impulses in the time domain corresponds to a train of impulses in the frequency domain as well. So that's one of the important results that we learned here. And more importantly, if the train of impulses is in the time domain is located capital N samples apart, in the frequency domain, these train of impulses are going to be located 2 pi by n apart in the frequency domain.